Imagine a completely separate reality floating just 1 millimeter away from your face. It contains its own stars, planets, and perhaps even its own observers, yet it remains entirely out of reach. We cannot perceive this neighbor because light is a prisoner of our specific dimension. It travels through our space, but cannot leak across the gap, leaving us effectively blind to anything outside our own universe. However, one force operates without regard for these boundaries. Gravity travels between dimensions, meaning a massive structure in a neighboring universe can exert a physical pull on the matter inside ours. If a multiverse exists, our best chance of finding it isn't through telescopes looking for light, but by searching for the invisible signatures of an external gravitational influence. In 2013, the European Space Agency released data from the Planck Telescope. This mission was designed to map the cosmic microwave background, the residual heat left over from the very first moments of the universe. This map shows the cosmic microwave background. Standard physics predicted heat would be distributed evenly, yet the data revealed a startling lack of uniformity. The most prominent feature is the Eridanus supervoid, a cold spot spanning 1.8 billion light-years where 10,000 galaxies are simply missing. Within our current understanding of physics, gravity is too weak to have cleared a space of this magnitude since the Big Bang. Additionally, the laws of thermodynamics suggest that heat from surrounding areas should have moved in to balance this temperature gap long ago. Because no internal mechanism can account for a void this large, the cold spot suggests a physical interaction with something outside our reality, a mark left behind by an external force. In 2006, physicist Laura Mersenne-Houghton published a mathematical prediction for a massive cold spot in the early universe. When the Planck map arrived 7 years later, the anomaly was found in the exact location her math suggested. Her model proposes that our universe is one of many bubbles floating in a larger medium. In this view, we are not an isolated system, but part of a crowded environment where universes occasionally drift into one another. According to this theory, when two universes approach, they don't collide like solid walls. Instead, the gravity of the neighboring bubble reaches across the gap, pulling on the edge of our own. When our universe was young, it was composed of a hot, dense plasma fluid. The model suggests that an external gravitational pull acted like a siphon during this phase, drawing away the raw energy and gas needed to form galaxies, and leaving the Eridanus supervoid in its wake. If this siphoning occurred, the cold spot isn't just empty space, it's a site where matter from our reality was drawn into a parallel dimension. This may not have been a single encounter. In 2010, computer models scanning the cosmic background radiation identified 4 concentric rings hidden within the data. These rings suggest that our universe has been compressed and released multiple times, indicating a history of repeated interactions with neighboring bubble universes. Further evidence comes from the dark flow, an observation of 1,400 galaxy clusters moving in a highly specific, coordinated direction. These clusters are traveling at 10,000 kilometers per second toward a single point. This movement cannot be explained by any mass within our observable horizon, implying a gravitational source that exists entirely outside our universe. Additionally, instruments designed to record the faint background noise of the cosmos detected the space roar, a radio signal 6 times more intense than the combined output of every known star and galaxy. The rings, the coordinated movement of galaxies, and this unexplained radio intensity all point toward a universe that is being pulled, squeezed, and influenced by a parallel reality. In 2012, researchers at CERN confirmed the existence of the Higgs boson. The specific mass of this particle provides a clue about the underlying stability of our physical laws. The data suggests we exist in what physicists call a false vacuum. This means our universe is like a ball resting in a shallow ditch on a mountainside. It stays in place for now, but it is not at the lowest possible energy state. A sufficiently violent interaction with another universe could provide the energy necessary to knock the ball out of its ditch, causing our reality to tumble toward a deeper energy level. This transition would create a bubble of new physics expanding at the speed of light. Inside this bubble, the forces that hold atoms together would change, leading to the immediate disintegration of all matter. This suggests the stability of our universe is contingent, an interaction we cannot see or predict, has the potential to alter the rules of our reality in an instant. There is a certain weight to the idea that our entire existence relies on the absence of a random, multidimensional bump. But it also highlights the reality of our position. We are passengers on a journey through a vast system that we do not control and cannot fully map. The forces pulling on our galaxies and shaping our voids are far larger than our daily anxieties or the choices we worry over. We exist within a scale of physics that renders our individual stresses secondary to the mechanics of the cosmos. Since the outcome of these cosmic shifts is entirely out of our hands, there is value in simply observing the display.